your chairman. I'm Mike Eaton. I've been involved with the nanomed area now for the last decade, and I am retired. My wife doesn't believe it 1 minute, but I'm lucky today. We have quite an interesting CNS program, really. I haven't got a lot of experience in this, although I worked for a company that made Kepra, which it does involve the CNS. And the first speaker is Mira. I've known her for many, many years. And
too many.
not too many. And she's come all the way from Tel Aviv to entertain us, I'm sure.
Shall I use that? If I'm moving? Oh. And how do I
okay, there's no problem on that. That's the laser, left and right. So that's forward.
Okay. Okay, if I move, I hope you will hear me. I will speak loud. Okay, so good. Do you have one? Doesn't matter.
You're okay. You carry on.
Okay. Good morning to everybody. Following the discussion and sessions that we had yesterday, I want to, in a way, I don't want to delude you, but I want to put things in well-defined orders. And we are going to talk about disease signature and towards precision medicine. But the question is personalized precision, disease signature. Do we really have it? Do we really know what it is? And the question is that I'm not sure, and I will try to show it to you. But I want to look on, disease signature and precision or precise medicine in a very accurate and broad band, like, to see the whole picture. And the question that I already raised is, could we really define what is precise disease signature, or even disease signature, or are personalized medicine and precise medicine the new buzzwords? How much of this can we really achieve? And when I'm talking about that, I'm talking on the broadband. As I said, I want to look on the micro and macro environment. I want to look not only on the biology, not only in the genetics that we actually know more nowadays, but I want to look on the physical and mental environment. It means our healthy or patient, where does he live? What is his cultural or physical environment, his mental status, and so on. So it's as much as I can capture to know about this guy in order to define a real precise or personalized signature. And we want to do it right. We want to do it unlike the big criticism nowadays. We want to do it in a reliable, responsible way, replicable, reproducible, all those huge criticisms that we have today about all publication. And that's what I want to share with you. And actually, the reason I put this book is to converge all our knowledge and all that we know about this guy that we want to define his disease. So just as an example, to give you, I think one of the big threats or maybe opportunities of our century is a healthy aging. And when I'm talking about that, I want to look. Could you still hear me when I'm moving? I want to look on. Can you hear it back? It doesn't matter. No, we can't. Okay. I will try to stick to one place.
Maybe if somebody could come and help and take this headset off me.
Okay. Is that possible? I don't want to lose the time. So, okay. So anyway, we want to look on the clinical data. We want to look on the physical and mental environment, like the people are dancing there. I mean, like, is he immigrant? Is he, okay. This is an experience, personalized experience.
This is an informal. And could you put that in some pocket?
Sure, I have a pocket. Okay. Okay, is it okay? Can you hear me? No. Okay. We don't need the mic. Okay? Okay, perfect. So we want to look, as I said, on the clinics, on the knowledge that the academia has to our specific disease, and even in addiction. For example, elderly people, they take medication or alcohol or drugs a long time, so they get addicted. So could we look on all the environment and then try to bridge using all the tools and knowledge that we nowadays have? So it's a big target, especially when we are talking on our analysis tool nowadays that, as I said, are so criticized. So that's just one example. And yes, nowadays more than ever, we have to keep the regulation and the privacy and the ethics and all that. So this is one of our big aims, and this is a project that we are going to do with the United States, the EU and United States, and I will tell about that later. But this is a big, broad goal. But what are the barriers? And just one thing, I was looking, we did a literature survey about disease signature. And out of millions of papers, we found just 108 papers that quoted disease signature in any way. So it's very, and mainly, I don't want to go because we are very short on time, only with one marker, and we nowadays know much better, and mainly in oncology or neurology, not any other disease. So it was really, in a way, very disappointing. But that's what we know today. But I want to go and talk further about what we are going to do. So we want to define this, as I say, disease signature, but we want to use not only the data that we have, but rather to combine data of various hospitals, even across nations. And this is another very huge challenge because each hospital, even each department treats differently, has different codes, has different treatment. So all that is big barriers, but we want to use whatever is available out there. So, one example that we did it already is the Human Brain Project. I'm part of the Human Brain Project, and actually I'm leading the medical informatics, and that's exactly what we want to do. We want to combine all available data and see whether we can be better in treating neurology disease. So that's what we did. We wanted to define brain disease signature, and we have nowadays 5 hospitals, and I can tell you it's a nightmare. You cannot do it. First of all, just to embed them, to bring them on board, but then each one has different definition, lots of missing value, lots of mess-ups, and we don't have really the tools to do that, but we'll talk about that. So we really want to embed and bridge and create all the needed technology to do that. Just as an example, another barrier is big data versus small data. We are talking about big data. But this is very short example. Just for one voxel, I wouldn't go because we don't have time, we will need 30 billion people. We will never have it. So if we want to provide personalized or precise medicine, we need to develop tools to treat and predict reliably small sets of data. Another example, which is a known EDNI database, the American Alzheimer database, which more than 2,000 papers were published about this database. And when we took it, because we wanted to do as a preparatory analysis to the hospital, we defined and we found that the missing value is the best predictor. That means that the analysis that was done about that, so versus, and it's naturally, if the doctor doesn't send you to specific test on Alzheimer, it means he assumes that you don't have Alzheimer. So it's very sad. Here I just showed the Alzheimer's disease, mild cardiac impairment, and cognitive impairment, and the normal. So we took this data, we developed tools to do the right imputation. We took just the full records and we analyzed it, but it's a huge barrier. If you can see here, without doing anything, 84% is predicted just by the missing values. So it's outrageous. So I just want to raise your awareness to these barriers. So we developed a tool to analyze, and I'm short in time, to analyze the Alzheimer's disease, and we developed something which is called 3C. And the idea is to start from the knowledge of the doctor, the physician, and to take all parameters upon his decision, what he thinks this patient has. Then we go the second stage and add to that and do another analysis, which is a blind analysis about all the other features that could support the decision of the doctor. And then we add up the biomarkers, the imaging, and so on, and that's the way we succeeded to do that, and I'll show you the results. So if somebody is interested, I can't go into all the supervised and unsupervised analysis that we did, but the idea is to start from the knowledge, embed the knowledge, add the analysis, and end up by the biomarkers. So that's what we did. And actually, this is on the ADNI database. As I told you, in the beginning, they had 5 assignments: normal, Alzheimer, mild cognitive impairment, early and late, and SMC. And we were able to define, unlike what they had 5 assignments, we were able to define new 10-1, new subgroups. So I won't go, these are the new subgroups. Anybody that wants to look at that is very welcome, and we can see here also what are the major parameters that define this new subtype. But I want to show you what we did, and this is really running now. So the lower part are the 5 assignments that the Alzheimer Databank, the ADNI had. These were the bottom one. And the top one are the new 10 that we defined. And you can see the separated 10 U1 versus the 5 which are very combined into them. And luckily enough, again, I can't go into that, luckily enough, we defined that these 2 are actually were unknown, new one. And this one, the bottom one, had also, we found a paper that was published in Neurology in 1996 relating to this subtype without them knowing that this subtype is special. And we are nowadays in the clinical trials with this group who published the paper, and we retrieved the data, and we are trying to see whether we can come up with something, and we are going into clinical trials again now with the new group. So this is just one example that, yes, we can if we do it right, and we have to do it right. And I just want to give you another very, very short example about Parkinson's disease. And the reason I'm giving you this example, because this is hospital data. So we are working 2 years already with hospital data of our Tel Aviv hospital. And again, we thought that it's in-house, and we know everything, and we know the doctors and everything, and we are working 2 years on cleaning the data and adjusting the data and preparing the data. And just to show you the development of the Parkinson's disease, so actually we want to be earlier. We want to be as early as the first symptom, and this is our main goal. And so just to you, the part of you that are doing this analysis, so after cleaning the data and after the imputation and after taking out the missing values and after changing everything, we were trying to analyze something very basic, like the genetic lags and GBA versus which are known as causing Parkinson, at least at the Ashkenazi Jews, and versus 4 very basic cofactors, which are age and so on, as you can see here, if you can read it, the BMI, the age, and so on. So it's very basic, and still, if you look at that, you see how many parameters. We had 2,300 hypotheses that we have to filter and to filter and to filter and to analyze. I wouldn't go into all that, but you see in the upper part, those are the, above the line, those are the real correlated, which, again, it's a very low number. But the outcome, I want to go to the outcome, and the outcome regarding the Parkinson's disease that we were able to identify is that if we are talking now about, the LARC versus the GBA, we didn't relate to the other. So the GBA, for example, when you give dopamine, the people are more sensitive to hallucinations, and their smell tests are less, and the GBA is performing different. And those are the early symptoms that we are looking on first, regarding the treatment, and then versus the treatment, how could we optimize the treatment? So when I was talking early about improving your quality of time or aging, that's what I mean. And again, I would be very happy to discuss with everyone in details these outcomes. So just to summarize, so we have our next big step is big data towards healthy aging, not longevity, but rather quality of life. And we are trying to work with the United States as part of the chamber. We are part of the NSF Center, working on the veterans' data. The veteran data is the huge data from the age of 18 till death. And we will try to do all that, starting from the data, the clinical data, adding to that the environmental data, the socioeconomic, the environment where those people lived through their lives, adjust the whole big data and analyze it the way I showed you. So this is, for now, I just wanted to give you at the end, as an aperitif, this is the Dead Sea. And the interest, what did I do? No. The interesting thing about the Dead Sea is that I just found out less than a month ago that through all the generation, all the registries that we have at the Dead Sea, even not one Parkinson or Alzheimer was found, 0. That means a lot. And just to give a very short explanation, because it has 6% more partial oxygen, it has bromide and magnesium, which relaxes the people. The sun is safer. It's unpolluted air, and we know already today that Alzheimer is influenced by polluted air, and non-aerosols and so on. So I think we can take a lecture from nature. Thank you very much.
Somewhere.
It's okay, we hear you.
Oh, it's below me. It's all right. I got it.
Thank you.
I'm sure. Okay. Thank you for that talk. And the data is fairly sound, is it, in terms of the oxygen and pollution?
Yeah, we next meeting will be at the Dead Sea.
Okay. Okay. Any questions, please? Patrick.
Thank you very much for this interesting presentation. Now, our legislation, governments, etc., they pose a heavy emphasis on the confidentiality, privacy, etc. And this is something that potentially directly conflicts with your interests. How do you handle this challenge?
So this is a huge barrier. It's a right one, but it's a huge barrier. There are, and if there are computer scientists or data people here, you can do distributed, you can compare averages, you can put a server in each hospital and analyze there at the same way, and then just compare analysis. I can't tell you it's the same like having the whole data as in one place. But I don't think nowadays even though all the security and privacy and so on, that we can really take data out of one hospital and combine it with another and put it in a safe place. It will. But while saying that, I think we have to develop more tools, not only to small data versus big data, but we have to develop more tools. How do we combine outcome of different sites, and how could I make it reliable, the comparison and the outcome? It's not simple, but I think still we are in the level of cleaning the data and combining the data of one hospital versus the other. The doctors are still writing different codes, different assignment. They don't write everything. They don't embed each parameter. It's really, I mean, it's a nature that we have to change, or a culture in education that we have to change.
Could I ask about the bins? You've got Alzheimer's going into 5 bins. How does the algorithm work that bins them? How do you get the interface? They're not sharp bins, I take it.
Well,
you have Alzheimer's, you have 5 categories. How do you precisely do those at the boundary? You know, between the categories, you know, are they clear boundaries?
No. And this is, I mean, again, I was talking earlier about reliability and replicability. Again, the threshold is very sensitive. Depends how you put it, as much as you have better tools. And you will be better in predicting. And I presented there the FDR. FDR was developed by Professor Benjamini, and he was the only Israeli, but I think the only statistician that was quoted in the most quoted papers ever in Nature, because he built this threshold. And this threshold can enable us to later on to provide the reliable data.
Any other questions? No. Okay.
Thank you very much.
Thank you very much.